All right, so the big thing here is that we have to understand that the energy, the mechanical energy that is, at the beginning of the ride here, or the toboggan to the hill, okay, is going to be the same as it is at the bottom. It's not going to be in the same forms. Okay, at the top of the hill, more of the energy is potential, less of it is kinetic. At the bottom, the situation is reversed. We have more kinetic and a lot less potential. Okay, so what we have here is that we know energy is being conserved. So EI equals EF. Right? At one point, okay, we're 30 meters above the bottom. So we know we have a hill, okay, and we know that at one point, it's 30 meters above the bottom of the hill. At this point, that's my toboggan, okay, at this point, it's moving at 14 meters per second. So this is part of my initial mechanical energy. Do I have kinetic and potential here? I do, because I'm moving. It gives me a velocity or a speed, so I know I have kinetic, and it tells me I'm 30 meters above the bottom. As a result of that, I have potential as well. Okay, so I can say that there's initial potential and there's initial kinetic. All right, the other position, we're told we're looking for how far above the bottom, so we would have to assume we're not at the bottom. Okay, would this thing be when it's moving at 23 meters per second? So does it have both kinds of energy, potential and kinetic at that spot as well? Most likely, right? They wouldn't ask us to calculate the height if the height was 0, right? So we would have to assume that it's moving, so it's got kinetic, and it's still above the bottom, so it has potential. So we would say EPF plus EKF. Okay, so what I'm looking for is the final height. I have the initial height, I have the initial speed, I have the final speed, right? Those are the things that I have, right? I don't know the mass of the toboggan, but do I need it? I don't. It's going to cancel because it's in every term. We'll see that in a minute, okay? All right, so the next thing I want to do then is I want to put in my formulas for each one of these terms, okay? So I have m times g times h initial. That'll be my EPI, okay? My initial kinetic will be 1/2 mvi squared. And then I'm going to have my final potential, so mghf, plus 1/2 mvf squared. Now, it's important for us to remember that this is what we are looking for, right? We're looking for the final height of the toboggan. Now, as I was saying, mass, m, is in every single one of these terms. That means everything in here is being multiplied by m. So does it matter what m is? Okay, it doesn't. If a question doesn't give you the mass, then you probably don't need it. Okay, most of the time on an exam, I would tell you what the mass of this object was, even though you don't need it, just because people feel more comfortable with it. Okay, I think I remember saying in the podcast there that I once played a trick on some kids. We had gone over this idea that mass canceled like 100 times, and then I gave them their unit exam. And a kid came up and he said, "Mr. Cooder, I think you forgot to put the mass on this question." I'm like, "Oh, did I?" "It's 100 kilograms. It was a roller coaster." "It's 100 kilograms. He kind of looked at me strangely and sat down. Then a few minutes later, another kid came up. "Mr. Cooder, there's no mass for this question." "Oh, it's 100,000 kilograms. And there's a few people out in the class who heard this and they're chuckling because they realize what I'm doing. They realize mass doesn't matter. And these two kids are going, "I gave them 2 different numbers. We're so screwed." Okay. It's like, and then finally I went, "Look, guys, remember, mass doesn't matter. You can use whatever number you want." Okay, but in the end, mass doesn't matter. Okay, so the next thing I'm going to do then is I'm just going to cancel all the masses. It's one less thing that I have to move around when I start manipulating the formula, so it's nice to get rid of it. Okay, so I'm looking for HF. I want to move this whole thing over here. How would I do that? Yeah, subtract it. I'm adding it right now. Okay, so I'm going to move my next step down here. So I'm going to have GHI plus 1/2 VI squared, because I've canceled the masses, minus 1/2 VF squared equals G times HF. All right, that's what I have left. I've subtracted the final kinetic energy over to the other side. I still need to get HF by itself. What do I do with G? divide it over to the other side. All right, so it looks like we do a lot of algebra in this question, but really we don't. We like subtract one thing and divide something else. Once in a while we have to square root if we're looking for v. Okay, it looks like a lot of stuff, but it really isn't. All right, now I need to plug in my numbers. So I'll have 9.81 times the initial height, which was 30 meters, plus 1/2 times my initial speed, which was 14 squared, minus 1/2 times my final speed, which was 23 squared, divided by g, 9.81. All right, the g's don't cancel here. Okay, there's one on top, one on the bottom, but there's separate operations. All right, that's going to give me the final height of the toboggan. Now, when you punch this in, don't try and do it all in one thing with a ton of brackets, because that gets really messy. You make one typing error and you're done. Okay, you might not even realize you made a typing error and then you have the wrong answer. So I do this one piece at a time. I go 9.81 times 30, and I hit enter. And I got that part done. I double check that I typed it in right. Okay, now I'm going to add to that 0.5 times 14 squared. All right, I did that part right. Good. Now I can enter in the next part. Minus 0.5 times 23 squared. Okay, I entered that right, hit enter. Okay, and then I'm going to divide by 9.81. Okay, better to do it one piece at a time. Okay, a lot less likely to make a mistake. And if you do make a mistake, you can go back to the number from the last step. You don't have to re-enter everything that way. Okay, so I got 13 meters would be my final height. Okay, that one makes sense? Looking kind of familiar? Okay. Try this one. Same idea, okay? Anything that's moving because of gravity can be a conservation of mechanical energy type situation. So in this one, we got a car that drives right off of a cliff. Not something you would do, okay? You shouldn't do, all right? But it was the best possible ending to Thelma and Louise. Oh, it is. Like, it's the best movie. I love that. I hate that movie. I was the only person in the theater who cheered. And then I got a lot of dirty looks. I got a lot of dirty looks when I cheered because I was so glad the movie was going to be over because I can't stand Susan Sarandon's voice. It just grates on me. Anyway, if I drive off of this cliff, okay, we are looking for how high the cliff is. Okay, so we don't know what its height is, but we do know that they drive off at 25 meters per second. All right, when they hit the ground, so down here at the very bottom, they are moving at 53 meters per second. All right, those are the things we know. Let me give you guys a few minutes to see if you can get that one figured out. All right, so if you drive off of a cliff, do you have potential energy? Can you fall? Yes, that's an important thing to know. If you go off a cliff, you're going to fall, so you have potential energy. Okay, so we have potential energy, and we're moving at 25 meters per second, so we also have kinetic energy. All right, so we're going to say EI equals EF again. Okay, and we know that at least at the beginning, there is both potential as well as kinetic energy. What about at the end? You only have kinetic. Okay, there can't be any potential because you're at ground level now. You can't fall any further than that. All right, unless you dig a hole and jump in it. Okay, which we're not doing. Okay, so ground level is as far as we can fall. Okay, so we're going to have equals EKF. All right, now I want to plug in my formulas. Okay, that's always my next step. Guys, these are very like find the pattern and replicate the pattern kind of questions. All right, so we have M times G times H initial plus 1/2 MV initial squared equals 1/2 MVF squared. Okay, we are looking for the height of the cliff, which means we're looking for HI. So what should I move? Okay, before I can solve for H, what do I have to do with this? I have to subtract it over the other side. All right, so what else can I do? Can I get rid of the M's? Yes, all right, so let's get rid of the M's, okay, and subtract our 1/2 VI squared over to the other side. So we're going to have GHI equals 1/2 of VF squared minus 1/2 VI squared. All right, then we just divide both sides by G, and we've got our initial height okay, to figure out. So when we plug in our numbers, that's going to be 1/2 times 53 squared minus 1/2 times 25 squared divided by 9.81. Okay, and divided by 9.81. All right, so our initial height here, this cliff, was 111 meters, which is pretty high. Okay. All right, questions on how that one worked? Everybody reasonably okay with that one? Guys, like honestly, I am not going to ask you anything different on your unit exam than what we're doing right here. Okay? The question on the unit exam will be like the toboggan or this cliff or a roller coaster or something like that. It's just going to be EI equals EF, solve for one of the things. Either it's velocity or height, initial or final. Okay? It's going to be just like that. So if you can, kind of get this pattern figured out, they all work pretty much the same way. All right, last one. I want you to try this one. Okay, so the skydiver jumps out of a plane moving at 90 meters per second, 10,000 meters above the ground. How fast will the diver be falling when he is 8,000 meters above the ground, assuming he has not opened his parachute yet? Okay, if you jump out of a perfectly good airplane, you have both kinds of energy, unless, of course, the airplane is on the ground. But even then, you have to jump out of it. You would probably fall from the plane to the ground, even if it's only this far. Okay, so in the initial instance, we would have both kinetic as well as potential energy. Okay, do we have kinetic and potential in the second point? Yeah, we're still 8,000 meters above the ground. All right, so we have a situation where there is initial potential, there is initial kinetic, and there is both at the end as well. All right, so plugging in our formulas here, we got m times g times hi plus 1/2 mvi squared equals mghf plus 1/2 mvf squared. And we are looking for how fast they'll be falling, so that's this, at the 8,000 meter mark. All right, first thing, let's cancel off all of the m's because we don't need them. And we weren't told what their mass was anyway. So I'm going to move the GHF over to this side. So I'm going to have GHI plus 1/2 of VI squared minus GHF. Everybody all right with that? Okay, and that's going to equal 1/2 of VF squared. All right, what do I have to do with the 1/2? Divide it over. All right, that gets me VF squared. Do I want it squared or normal? Normal. What do I have to do to both sides? Square root. Okay, so what that will leave me with is this. 9.81 times 10,000 meters plus 1/2 times 90 meters per second. And that's squared minus 9.81 times 8,000, all divided by 1/2 and square rooted. Okay, so okay, divided by 1/2, square root that. Okay, so they will be moving at 217 meters per second at that point. Is that pretty fast? Yeah, it's quite fast. All right. If they go much faster than that, they'll break the sound barrier, which will not work out well for them because they actually won't break it. They'll just smash into it. Okay. So did we get going on any of these when you were here with the sub? No? Okay. I want to talk about efficiency before I get to this. Okay, but then we'll spend some time working on this. Like say tomorrow, we'll do our unit exam review. Okay. All right. Well, so the big thing here, guys, about efficiency is how well or what percentage of the work or energy that I put into something do I actually get coming out the other side doing what I want? Okay, how much useful work is the energy or work I put into something doing, right? So as an example, if I put, let's say, 10,000 joules worth of fuel in my lawnmower and then I mow my lawn, but when I mow my lawn, I only end up getting, let's say, 5,000 joules worth of work done. What efficiency is my lawnmower working at? I put 10,000 joules into it, but I only got 5,000 joules of useful work done. How efficient is it? 50%. Okay, 50% of the energy I put in actually did what I wanted, which means the other 50% was wasted. Okay, it was sound, heat, and whatever else that ended up going off into the environment. Right? And that's the reality of things. Nothing is 100% efficient. We've been doing all these conservation of energy problems where everything's 100% efficient, but that's in the perfect physical world. In the real world, that doesn't happen. Okay? Now, to give you an idea here, okay, if we look at like something that we use every single day, your car. Okay, your car runs at an incredibly low efficiency, even if it's a modern vehicle, okay, with, and it's all tuned up and everything and it's working great, it still runs at an incredibly low efficiency. Okay, if we look at the parts of a car here, okay, I've got, if I put in, a bunch of, let's say 100 joules worth of energy, let's just say that's what we got, okay, or 100% of the energy, okay, the exhaust system will waste 33% of that. That means that 33% of the money that you put into your car in fuel goes right out the tailpipe without doing anything effective. Okay? It just turns into heat, and that heat is radiated away into the environment. All right? So if you put $100 worth of gas in your car, understand that $33 of that goes right out the tailpipe without doing anything useful. Okay? Your cooling and heating system. That would be your radiator, water pump, okay, circulating the coolant that essentially keeps your car from melting down because it's so inefficient, right? Your car is so inefficient and generates so much useless heat that it has to have a whole separate system that uses energy to keep it from destroying itself, right? So the water pump and cooling system uses another $33 worth of that $100 in fuel. Right? You haven't gone anywhere yet. All your car is doing is running and not destroying itself, and you've used 66 of your 100 hard-earned dollars worth of fuel. Okay? Your drivetrain, that would be all like the physical parts that turn, transmission, all-wheel drive, limited slip differentials, all that kind of stuff that might be in your car. Okay? That stuff has friction in it, right? And energy is lost to friction and heat and sound and whatever else as you drive along. There's another 10%. Right? We're now up to 76%, 3/4 of the money you put into your car, and you haven't gone anywhere yet. Okay? It's a lot. Your accessories, about 4%. That is if you do not have a heavily modified vehicle. All right? If you've got one of those stereos that's, announcing the end of the world, okay, like the guy that drives by my house all the time, as he goes by, it's like crazy loud, like things shake in my house. Okay, that probably uses a little more than 4% of the energy. He probably has 2 alternators generating power in order to power his gigantic subwoofers. Okay, the really ironic thing is he's driving around in like a beat up old Mustang that's probably not worth as much as the stereo inside it. Okay. All right, so there's another 4%. Okay, internal friction, 6%. What you're left with is 14%. So an average passenger vehicle, not a truck, okay, like let's say a small SUV or a mid-sized passenger car, runs at 14% efficiency. So you put $100 worth of gas in, 86% of it is wasted. Okay? Doesn't do any driving of the car forward. We accept that every day. You get in your car and accept that it's only 14% efficient. Okay? It's unreasonable, like you think about it, right? You wouldn't go to a doctor who was only right 14% of the time, right? Not a whole lot. I mean, the bigger you get, the less efficient, or the more performance-oriented, the less efficient the car is going to be. Hybrid vehicles and electric vehicles are more efficient than this. Okay, hybrid vehicles marginally more, electric vehicles a bit more. Yeah, exactly. This is like an average person driving. If you drive like me, that number is lower, okay? Because I drive aggressively. Okay? The best defense is a good offense. So I drive defensively / offensively. Okay? But you shouldn't do that because it's not a good idea. But yeah, it all depends on lots of factors. Okay? Yes, would an electric car be more efficient than this? Yep, an electric car is more efficient than this. There's no arguing that an electric car is more efficient. Okay? But it still has to do the same job. It has to take you from A to B. All right? A lot of people switch to electric vehicles for what reason? What do they? Right. They think they're saving the environment. Are they? No, they're not. It's unfortunately not really true that you save the environment by driving an electric car, especially in Alberta, where the majority of our electricity is produced by doing what? Burning coal. Yeah. Yeah, so you're not really reducing your carbon footprint a whole lot by driving an electric vehicle in this province anyway. Okay, if you lived in a place where all of the electricity was produced in solar and hydroelectric and whatever else, then you would be reducing your carbon footprint a little bit. But in Alberta, driving an electric car does not reduce your carbon footprint at all. Okay, you're just making the coal-fired electrical plants work harder. Okay, so they're putting your share of the gasoline emissions that you would have put into the air in the form of coal emissions instead. You're not saving the environment in Alberta by doing that. Okay, is it more efficient? Yes, it is. Okay, but it's still got to get the energy from somewhere. Right now, if you had a big giant solar panel on your roof and that's how you charge your electric vehicle, then yes, you would be reducing your carbon footprint in that case. Right? But here's the other thing to consider. Electric cars need batteries. What's in the batteries? Really bad stuff. Okay, like really, really bad stuff. So when an internal combustion engine car dies, it goes to the wrecker, and there's just a lot of metal. Okay, they drain like the fluids out and whatever. They're not terribly harmful. The electric car goes to the boneyard when it's dead, and you got to somehow get rid of all the heavy metals and other horrible stuff that's in the batteries. So there's always a trade-off. Okay, I'm not saying don't buy an electric car. I'm not saying that. They're good, okay? But they don't always do what people think they're doing. Okay? Buy it for the right reason. Buy it because you want it. Okay? If you're trying to save the environment, you might not be. Okay? Just putting that out there. Okay? I'm not against electric cars. Just if you're buying one, know why you're buying it. Okay? All right. So systems with moving parts are always going to lose energy as heat, as sound, sometimes as light, okay? Things like that. Those are all evidence that energy is not being used to do the express purpose. Right? If we're looking at, let's say, light bulbs, for example, okay, through your guys' lifetime, light bulbs have evolved a lot. Okay, when I was your guys' age, there was one kind of light bulb. You screwed it in, it had a filament in it, and that was it. That was the only kind of light bulb you could get. Right? But then they came up with compact fluorescent ones, those ones that look like a little spiral. Okay, those are more efficient than the old-fashioned Thomas Edison incandescent bulbs. Okay, the old-fashioned incandescent bulbs use 60 joules of energy every second. If you have a 60-watt bulb, it's 60 joules per second. If you get a compact fluorescent, you can replace that 60-watt bulb with a 13-watt bulb. Are you saving energy? Yeah. In fact, more than like 75% less. Okay, it's quite a savings. And now you can do even better than that by getting what kind of bulbs? LED, yeah. You can replace a 60-watt incandescent bulb with a 4-watt LED. Okay, that's a huge, huge savings. All right, so they're more efficient. They're doing the same job using less energy because they're not producing heat. An incandescent bulb, incandescent means light from heat. Okay, that's what incandescent means. So if you had like an old-fashioned bulb and you turned it on, within seconds it would be too hot to touch. Right? A compact fluorescent bulb, they're warm, maybe a little bit hot to the touch even after they've been on for hours. An LED, doesn't matter how long it's been on, you can reach up and grab it. Okay, they're always cool because they don't produce a lot of heat. Okay, that's why they're more efficient. They're just putting out the kind of energy you want, not a bunch of other kinds you don't want. Everybody with me on that? Okay. All right, so efficiency Okay, very simply, efficiency is calculated by taking the amount of work that was actually done that you wanted and dividing it by the amount of energy you had to put in to get it done, right? Just like you would calculate your percentage on a test. You take the number you got right, divided by the number that the test was out of, and you got your percentage. Okay? You do the same thing here. The amount of work that was done divided by the amount of energy that was required to do it. Okay? It spits out that little decimal, right? Like if it comes out to 0.85, it's what percentage? 85%. All right, so it's an easy calculation. You guys do it all the time when you're figuring out your percentage on a test or a quiz. Okay, same idea here to calculate efficiency. All right, so let's look at an example here. So let's look at this crane. All right, write this one down. This is a good example. Okay, give you a minute to write it down. This one here. Okay, the solution is kind of there, but I want to kind of walk you through it here. Okay, the toughest part of an efficiency problem is reading it properly, because sometimes it's worded in a way that it's hard to tell whether this energy is the input and this energy is the output. Okay, so you have to look at A, the numbers you're given, and B, the context of the question. All right, so we have a crane that lifts a load of construction materials from the ground to the second floor of a building. In the process, the crane does 2.3 times 10 to the 4 joules of work, or mechanical energy input. Okay, while doing 8.0 times 10 to the 3 joules of useful work or mechanical energy output. Okay, so if for efficiency, okay, we're supposed to take useful work and divide it by input energy, okay, which of the two numbers is always going to be smaller? Yeah, the output, the useful work, okay? The useful work that's done is always going to be the smaller number, right? So if you're looking at a question like this and you're like, I don't know which one's which, I can't tell from the wording, just look at how big they are. This number is 8,000. This number is 23,000, all right? If the 23,000 was on the top, this machine creates energy, which is impossible. Okay, according to the law of conservation of energy, energy can't be created or destroyed. You can't have a machine that creates energy. All right, so the smaller number is always the one on the top. So we would have then 8,000 divided by 23,000, okay, joules and joules, right? And that's going to give us our percentage of 34.8%. It comes out to 0.348, which is 34.8%. Okay. Okay, in the end, I don't usually ask for really big calculations to do with efficiency on the unit exam. My concern more is that you understand what efficiency is. Okay, so if something is very efficient, it's converting most of the energy that's put into it into what we want. Okay, if something is not very efficient, then it's wasting a lot of the input energy and not putting out a lot of output energy. Okay. All right, I want you guys to try 1 and 2 for right now. Okay, so they're efficiency questions. Okay, so what we were just looking at, remember that efficiency is, okay, useful divided by input. All right, so for question number 1 here, okay, we're told that it works with an efficiency of 15%. How do I need to write that if I'm going to put it in this formula? As 15 or 0.15? 0.15. Okay, I need to write it as the decimal, so 0.15. Right? And it's used to do 3.20 times 10 to the 4 joules of useful work. Calculate how much energy had to be put in by the combustion of fuel. All right, so we are looking for the input energy in this situation. So I'm going to manipulate by multiplying input over here and dividing the efficiency over. All right, so what I'll have is that the input will equal the useful work divided by the efficiency. And since we divide by a decimal, that always makes a number bigger. All right, so we have 32,000 joules worth of work divided by 0.15. And when we do that, we should get 213,333.3 repeating joules worth of energy. Okay, so just a matter of manipulation here. That's all there is to this. How many people are done 2? Okay, let's go over 2 as well then. Okay, so in lifting a car, the mechanical energy input, so how much energy had to be put into the hoist, is 5.61 times 10 to the 4 joules, okay? While the useful output energy is 1.96 times 10 to the 4 joules. Calculate the percent efficiency. All right, so in this case, I don't have to manipulate. I'm being asked for the efficiency. All right, so I'm going to take my useful work, okay? That was 1.96 times 10 to the 4, or 19,600. Divided by the amount of energy it had to be put in, 56,100 joules. When I do that, I should get 0.3493, which is 34.93%. Okay. All right, so tomorrow, make sure you come with some questions to ask. Okay, when we do our review, what kind of things are you going to want me to demonstrate again or review in a little bit more detail? I'll do the usual spiel, okay, where it's here's the stuff we went over, here's what's going to be on the test, but you got to come with some questions so you get a little more out of it than just that.